and the next session will be on sensors. Speaker, Trouble Risk, I hope I pronounced your name correctly, from Oculi Incorporated, founder and the CEO, and we'll talk about new architecture for visual AI. Thank you very much.
Thank you very much. Yes, an excellent question to my friend, colleague, Christoph there. And that's actually partly what motivated the work that we're doing, and I'll share with you here in a minute. But first, I wanted to thank tinyML for organizing this session. I'm personally a big fan of tinyML. And the reason for that is I hope we will partner with someone to produce the next generation of Arduino for a visual AI and vision technology. I want to share with you my personal motivation, what got me going in this technology space. I was actually working in this space early on in my career, but more recently, these are samples of my students building robots. And it's amazing because many years ago, I was building robots myself, starting with drones, and computer vision was out of the question for those kind of platforms. 30 years later, we are still having the same problem. So none of those robots deployed computer vision because it remains too expensive, slow, and certainly inefficient. And the big question consistently that haunted us many years ago is why? Human vision remains many orders of magnitude more efficient than any computer vision that I know of. And I'm talking about a full solution here, not the sensor or the processor by itself. And the reason for that really is, as Christoph pointed out, imaging sensors really generate a lot of data. So we've had this fundamental trade-off between the amount of data the sensor generates, how much power and time it takes us to process and get the actionable information out of it. And the trade-off really has existed for decades. And early on, when we decided to really tackle that challenge, we did a lot of trade studies and assessments. And we came up with these conclusions that I'm sharing here and really what motivated the technology that we've been developing. In order to solve that trade-off, you have to maintain that parallel processing and memory. And I believe in your talk earlier today, by the way, that a great tutorial, you emphasize that aspect of it. So you have to do some parallel processing, and obviously having a parallel memory is important to make it efficient. But we also have to make the sensor itself smart, and we believe starting at the pixel. Okay, so those were the fundamental conclusions we had early on. And we also realized that the sensor has to be programmable in order for, to be optimized dynamically, whether it's from the sensing aspect of it or also from the processing aspect of it. And if you are able to develop this versatile platform as an imaging sensor, then you can obviously deploy it in many different applications. So we no longer have to build one solution for one product and one application, and then do it all over again. So you build one hardware and use it in multiple cases. Lastly is we wanted to make the architecture agnostic of the sensor type, because today, CMOS visible imaging is the most commonly used. Tomorrow it may be infrared. You got time of flight coming online. So as the sensing modality changes, we also wanted to have the architecture kind of grow with it. And those two factors really are dominant for performance. The last two are dominant for economics. And this is why Oculi as a company is trying to commercialize the SPU, Sensing and Processing Unit. This is a single chip vision sensor that is truly software defined and smart enough to output the relevant information. And the pixel being the dominant building block in imaging sensor technology, it's no surprise that we spent a lot of time and energy on the pixel itself. And although the details do matter, and we've developed and fabricated over the years, and I'm meaning the research that I was involved in and leading at Johns Hopkins before Oculi, it has two basically components, what we call the front end, which is the sigma delta that feeds into a digital processing block. So in a nutshell, that's basically the two main components of the architecture. And even though it comes across as simple, and it is, I'll show you why it is very powerful. So I'm going to switch over to use cases that today are out of reach for tinyML applications, but tomorrow they may be with the SPU as the vision sensor. In this case, eye tracking, and we're trying to track the pupils. So I didn't want to, share redundant data, like Christoph shared earlier, where events were output based on motion. In this case, our technology also allows events to be outputted based on color. So we are tracking the pupil color in this case. And as you can see, the bandwidth reduction, well, meaning that that's the amount of the overall image that we output to the outside world. And you can see the significant reduction there. And if you were doing it based on motion, you'll be tracking more than the pupil in this case, as you see the eyelid moves. The even more compelling example is GLINT. So in eye tracking, GLINT is an important aspect that they want to track as well. In this case, you're getting almost a couple of pixels at most, versus having a full frame to start with. Again, if you're doing it based on motion, you're going to get a lot more events in this case. And by doing it based on intensity or color, you can significantly reduce the amount of data that you get out on the output. Now, I also want to share an example about the computation that are implemented in parallel. And this example is background subtraction. So in many imaging applications, subtracting the background, just like Zoom does right now in order to show that fake background behind me, right? It's subtracting my actual background. But if I move my hand fast, you start seeing the real background because the camera, is relatively slow in this Zoom interface. But when the background is not changing fast, you can actually extract the background very easily and then output the information that's relevant. Again, that's a very effective way. And there are very similar computations in image processing that you can implement on the SPU. I also wanted to share that for the larger ecosystem that has been focusing more on the machine learning side, that integrating the output of our technology would be relatively painless. I apologize for the videos here, but what we're showing here is that we can output full frame, but we can also output pixel intensity, not just spikes. And so we took an ML model that was trained on full frame. That's the left video that you're seeing there. And then we used the same model. We fed it to smart events, which is basically pixel intensities of only the events that we think are relevant in this case. This model was trained on counting, detecting people. And so the model worked fine even when we fed it a lot less data. Again, emphasis on being the bandwidth, the amount of data that the SPU, that our vision sensor shares with the outside world. Another data point I want to also share with the community is stereo vision. High-speed stereo vision is definitely not a tinyML application today because you take 2 full frames at a certain rate and you have to do image registration, extract the common features, and then generate depth. We've demonstrated now that you can do that based on the smart events, which again is a significantly reduced number of data points, and it allows you to do depth at a higher speed. In this simple example, we did the demonstration at about 700 hertz. Again, you're processing 20, 30 times less data per sensor. The last, but not one of my more favorite use cases examples is a demo we did for a customer on measuring rainfall to predict flash floods on roads, and obviously generate a warning and saves lives. But then when tinyML came out with the weather station challenge, I got even more excited. So, we didn't have the bandwidth to actually participate in the challenge, but we're happy to work with any teams who are working in that space and would like to assess what an imaging sensor like the ones that we have can do for a weather station. We believe you can ultimately have no moving parts, the SPU with a microcontroller, and it will be a pretty effective weather station. I'll leave off by saying that we've developed platforms to make our life easier in evaluating and demonstrating the technology, but also for our collaborators and partners. So if anyone's interested in getting their hands on one of these platforms, feel free to reach out to us and we're happy to work with you. I thank you for your time. And again, my personal motivation is to have an Arduino out for students and hobbyists and everybody alike that is, that can do some serious computer vision powered by our first product SPU, the S12. Thank you very much.
Thank you very much, Cheryl. Fascinating presentation. Please ask your questions in the Q&A window, and Cheryl, please have a look and answer them afterwards. I'll have one question as well, a bit more generic question. Maybe you could tell us what is the main bottleneck for you when you develop applications for this technology? So what takes your team most time to come up with a demo like that? And what is the main challenge when putting this technology to the market? Like when you have
Okay. Very good question. And coming from Intel, I know where you're coming from. The challenge we've had really, and I think, Christoph can speak for a similar experience, is that we're developing only part of the optimal solution, right? Our SPU optimally outputs the data that's relevant, but then we need a partner that actually can receive that data and then process it efficiently to demonstrate the full solution to the customers, right? Like today, I can tell you we have a long line of customers, but they all want to see a full solution, and we are only working a part of it. So we are actively looking for partners to do the full solution. Eye tracking being a perfect example of that.
Great, thank you so much.